Dr. Cordelia Schmid is going to be our next speaker. She's a well-known figure in the computer vision community, and she's primarily affiliated with Google and INRIA these days. She has previously been awarded various prizes such as the PAMI Longwin Higgins Prize, the Coendrick Prize, and other the Test of Time Awards. And she's been chair of CVPR and ECCV previously, and as well as the last ICCV as well. She's going to present the talk on this. Sorry, the talk on video reasoning and grounding methods, and present some of her recent work.
Okay, thank you for the nice introduction. So I'll share some recent results on video understanding and grounding. So to start with, where are we today? There has been very rapid progress recently with video LLMs. So for example, if you look at the results you get for video captioning in general, it works surprisingly well compared to what we had a few years back. And then also one thing is, I'll talk about what about benchmarks. Many of them are now saturated, and so it's important to create new benchmarks. And then just to give some recap, so this was work we did 2 years back. So it was for video captioning. We had text and time tokens were predicted as one consistent sequence, and we had large pre-training from untrimmed videos. And so basically the architecture we presented in this paper is still one of the mainstream architectures. You have a video encoder, a text encoder, and then you have a decoder which predicts the text. So it can be either one model or two different models, one encoder, one decoder. So there's kind of variances of this architecture. And then it's also quite common that now you predict the captions and the time stamps in one stream. And so this model was state of the art. And I just looked at what happened on this data set, which we used there. For example, here it's Q2, and you can see that there was a significant gain in performance, like plus 20% in the last 2 years. So you can really see that there is significant improvement. And then another example here, this was one work which we presented last year for video reasoning. So it was modular reasoning stages where we combined different reasoning steps. And again, at the time it was state of the art. And then if you look what happened since last year, basically the performance again went up by 15%. So it's really surprising how much the performances these days go up. So basically, I wouldn't say it's solved, but there has been major progress. And so I think the question which I want to ask today is what is still missing? So one thing is we need to have good and difficult benchmarks and look at reasoning-based approaches to really justify actually what's going wrong. So not just have video question answering, but also to see why these models produce these outputs. This is the first part of my talk. I present our recent Minerva dataset for video question answering with reasoning traces. And then in the second part of my talk, I'll show some recent results in video grounding. And why is this important? It's actually important to have a more detailed and verifiable description of the video so that you really understand what's going on. And then once you know which are the objects which really contributed to your decision, you can then use it to do some additional reasoning on top, or at least understand what actually was there to make this decision. So again, go away from these black box models. Okay, and I'll start with this data set. So this was work which has been done at Google DeepMind. And so here, what is the idea? The question which I asked in the beginning is video question answering solved. So here the question is, how many students does the teacher in the video ask to read from? The correct ground truth answer is 4, and the model answers also 4. And actually, we don't really know why this model gave this answer 4. And so we don't really learn much from this answer. And so what we want to do here is to additionally have this ground truth reasoning trace. So where you know, if you watch the video, I can see that the first interaction starts at 1 minute 20, the second one at 2 minutes 35, and so forth. So you can really see what was there to give this answer. And then if you look at here, the output is done with the model Qwen 72 billion parameters. You can actually see that somehow it gets the high-level AGA correctly, but the temporal localization is wrong. This is something which you observe. In many cases, the model gets it globally correct, but then basically localizes the events temporally wrong. And then if, for example, you have 5 instead of 4, it might miss it. And then if you look at these reasoning traces, you can actually see where the error comes from. And so basically what I said in the beginning, we just want to go away from this complete black box models and really see what the model is actually doing step by step. And then if we have these traces, we can also have some additional reasoning or verification on top. And this makes also the model more interpretable and assures that basically it's not just using some shortcut or bias to predict the correct answer. And so here, just a few videos of our data set. What we really want is to have complex multi-step reasoning in this video data, and then to have also correct model reasoning traces, which we can really use to assess the performance of the model. And here, this is a quite challenging question. I think probably most of you cannot answer it either. It's about gravitational forces. You have to watch the video, you have to really understand what's going on in the video step by step. And so here we have the question, the correct answer from 5 different choices, and then the reasoning trace, which really says what needs to be watched. So if you were, it's annotated by skilled human raters. If you watch the video, what really justifies your response and how would you get to this answering these very complex questions, right? And then for each of these reasoning traces, we have also annotated what kind of skills you need to answer them. So for example, you need temporal reasoning, complex reasoning, multi-step reasoning. And then we have different domains. So we have sports, we have vlog data, we have lifestyles, we have how-to videos, and so forth. So it's kind of quite varied. And here, a few examples. I just go through the example of approximately how long would it take the woman to knead the dough if she was working twice as fast. So the correct answer is 45 seconds. So you can see clearly, in contrast to many existing video data sets, just by looking at one frame, you cannot answer these questions at all. So you really have to go into the video and observe what's happening there. And then if you look at the reasoning trace, so the answer is 45 seconds, I watched the video and kept tracking how long it takes, and then you kind of describe where the different steps are. And then in the end, if she was working twice as fast, the model says you have to divide the final answer by 2 to get the response. Okay, and then the statistics, we have 1,500 questions for 223 videos. The video lengths have different durations from 2 minutes to 100 minutes, so the lengths are quite varied. And the reasoning traces are long and detailed. The mean number of words is 92. So you can see the red histogram distribution shows you how many words the reasoning trace has. So it's really very detailed. And interestingly enough, 99% of the time, the reasoning traces contain timestamps. So many of these questions actually require that you zoom to the correct location or temporal location in the video. What we don't have here, we don't have any spatial annotations yet, right? So we have this temporal reasoning, but we don't have any spatial annotations. Is something we're kind of currently looking into, if we could further improve this reasoning by not only having the temporal timestamps, but also adding the location of the objects in the image. Because if you, for example, look at counting, you would need actually to localize the number of instances in order to be able to see that the counting has been performed correctly. And then here on the pie chart on the right, you can see the distribution of the different domains. So you can see that it's quite distributed well between live vlogs, how-to videos, and short movies. And then one thing which is important, in many cases, if you add ASR to the video, understanding ASR in many cases really helps you to understand what's going on. And so what we wanted to do here is really concentrate on the vision modality and to make sure that with ASR only, we cannot answer the questions correctly. So if random would be 20%, as we have 5 multiple choice answers. And you can see here for different types of models that they all can't really go much above the random performance with ASR. So we guarantee here that basically A, the questions cannot be answered just by general knowledge, and B, not just with ASR. So this really guarantees that we need to have the vision to answer the questions, right? Because otherwise we have all sorts of biases from the language or just the way the question is answered. And then here, if you look at the state-of-the-art performance, so on the top we have open models. So here, Quen, which is currently one of the best, then Video Llama, Intern Llama, which are all Intervideo, which are all strong open models, and you can see that the accuracy for this multiple choice is around 35. And then if you look at the closed models, you can see that basically the performance is significantly higher. So this is actually something which is interesting to observe, that nowadays these closed models perform quite well. And so two take-home messages here is basically that these closed models are making very quick progress. So when we first evaluated the Gemini Pluto and Flash, and the latest Gemini model, there was a 10% increase in performance. So there's like really significant progress made on these closed models. And then the other thing, if you look at globally at the performance, there's still significant room for improvement, right? So if you look at human performance, while it's not 100%, because humans sometimes get these very difficult questions also wrong, we're at 92. It was done by several raters in parallel. They are trained, they have to be trained, or otherwise the questions are too difficult. And then we can see that there's still like a 30% gap in performance. So there's still like things we can do to further improve the performance. And what are the things which are actually not working? So one thing which the models really struggle is counting objects. So this is what I said before. Therefore, we need some spatial localization. So if you have 5 or 6 objects in the image, it's really, or in the video, it's really hard to determine how many there are. And then other problems are counterfactuals and state changes. So if there's state changes, it's really hard to see how well it does. Okay, and then all models perform best at short films. So I guess a possible explanation is that in the training data, there were many of these short films or similar things already observed. So this is obviously, I got this question, you don't know what the model has observed, so there might be some bias towards how the model was trained. But we didn't train the model to perform well in this data set, but it's an explanation. And then all the models, if you look here, they struggle most with the math question. So here you have the different pie charts for the different models. You can see that they all perform really poorly on math. So here in green, this would be human performance. And then in pink, this is Gemini. And then in green, Quen. So you can really see they all perform badly on the math questions. You can also see, I don't know if you can see it here, the different types of categories where it performs badly. So you can say, for example, spatial reasoning, it doesn't perform very well. And then also temporal reasoning, it doesn't perform well. And then counting, there's the biggest gap between the human performance and the performance of all the models, right? They all kind of go down. And so on the right, you can see the performance with respect to video length. You can see that if the videos get longer, the performance goes down. This is kind of explainable because it cannot take the number of frames which can take, there's a maximum number of frames which it can take as input. And so basically, if videos are too long, then the performance goes down. And we have some other work at CVPR where we show that if you have a way of pre-selecting the locations in the video which we'll have to pay attention to, we can improve over this. So there's like works which we can do to see how to improve over this. And then now basically this was the performance just on question answering, and what's actually most interesting is how do we assess this reasoning and how well does the model actually reason? Because it's one thing that you get the correct answer, as I said, but then you also want to know how the model got to this answer. And so these are these thinking models which actually at the same time output a reasoning trace and then the correct answer. So basically the reasoning trace, you can look at it. So here on the top, so we have categorized the reasoning errors into 4 different types. So the first one is temporal localization. You can see here the ground truth reasoning. And then if you look at the model reasoning, you can see that it makes a mistake in the temporal timestamps. There's something which the model often gets wrong, cannot really predict the temporal location very accurately. And then the second error is a perceptual error. So basically, it kind of gets it wrong what the game did. And then logical reasoning, so when it gets the logic wrong. And then the last one is completeness, that the trace is very short. And so there's a lot of work on this reasoning traces in text, but for vision, I think I saw a paper yesterday at the area chair workshop where people have started looking into these reasoning traces and using text-based methods. And then obviously here, so here we compared the different reasoning, the accuracy of the reasoning traces. We used the 3-point Likert scale. So Likert scale is like either correct, incorrect. Here we use 3 or partially correct. And this was done by humans. And you can see here basically the difference between the different models. So the red one is Gemini, and then the blue one is ChatGPT. And then the open models are a bit worse. And so you can really compare how they compare to each other. And you can see that basically temporal reasoning and perceptual reasoning are quite bad. Completeness is a bit better, which means that basically they all produce more or less long answers. And then obviously we cannot use humans all the time. So the question is now, can we actually also have some metric which automatically evaluates these reasoning traces? And the answer is actually yes. So what we did here is we use an LLM as a judge, which is actually something which is also used a lot in the text literature. And so here what we do is we give the LLM the ground truth and the predicted reasoning trace, and we ask it actually to produce this 3-point Likert scale, like to say if it's correct, partially correct, or incorrect. And so here what we did is we looked at how well different models perform for this task, and we can see that basically the larger the model, the better this correlation. So the Pearson correlation is in the column, in the last column. And you can see that basically for larger models, it performs better, right? So basically the correlation for a larger demo model is 59 instead of 31. So it has a higher correlation. And then Gemini and GPT-4 are a bit higher again. And interestingly enough, if we give also the visual input to the evaluation, it doesn't help, right? And so I guess this can be explained by the fact that it's just the extractor. If you give the video and then the ground truth and the produced reasoning trace, it doesn't give you any additional information. What you really want to do is compare the two text informations. And so basically the video in this case doesn't help you at all because you have already used it to produce these traces. It actually makes sense, right? And so we can really see that we get, with just using a standard LLM, we get a good performance for an evaluation, so we can really evaluate them automatically. And what we didn't do, what we could also do is train an LLM to see if this is correct, and this would be further improving the performance. And then here we evaluate this LLM as a judge on the different data sets, different categories. So if you look at perceptual correctness, you can see again, basically the ranking is similar to what we have observed so far for the accuracy of the multiple choice question answering, but we can also see that basically, for example, tempo localization is much harder and models struggle much more than for the other types of errors. And then if you look here, this is also interesting. So if you look at different of these open models, we can see that the performance on accuracy is comparable. But then if you look at the traces, you can see that actually Qwen2 produces much better traces than the other two models. And so actually I don't have any good explanation, but it's a different way of comparing these models. And you can really see that maybe it was trained on some of these thinking traces or whatever. I don't know exactly why it's better, but I guess the way it's trained is more prone to have good reasoning traces. And this means that basically it's something, if you look at what's going on or you want to understand what's really happening, gives you more information. Okay, and then this data set is available, and we hope that it will spur progress in this reasoning type of approaches, which I think is the next step. And text has shown that you can really massively improve the performance by adding this reasoning. Okay, and then the second part of my talk is on this grounded caption generation. So here, what is the idea? What we want is, instead of just captioning, or it could also be vision question answering, we want to have as output the caption. So woman is stirring something in the wok by using a spatula. And in addition, we want to have here, it's the grounding of the nouns. We want to have all the nouns grounded on the video. You could possibly also imagine that you want to ground verbs, but that's much harder because it's kind of an action which you need to assign to an object, right? So you can see here we have the wok correctly localized, we have the woman, and we have the spatula. And so, okay, so here, what are the ingredients to our approach? So we need to generate large-scale pre-training data. So basically, there's basically no data for this task. So we show later on that large-scale pre-training, as usual, helps. It's important. Then we design a model, an extension of an image-based models to spatial temporal grounded video generation. And then we also propose a new data set for this task so that we can really evaluate the performance, which is necessary that we can use it for training to fine tune. And then we also have a test set where you can compare the different pre-training approaches on. And so what do we do for pre-training? First, we localize in each frame or in a subset of the frames, for example, at 8 frames per second. We use either the GLAM approach to localize the objects or an open vocabulary detector, OVID. Any way of detecting objects in the image could be used. And then we caption these different objects. Then we extract from the generated captions the verb object pairs. And then we can use those to feed them into here an LLM Llama 2 to combine them into video level captions with tags. So we have them assigned to the different objects in the image. And then we can also alternatively apply LLMs on different captions. There's quite a few ways of doing this. We have compared them in the paper, and we can show that they make slight differences. But in general, what's important is that you localize the objects well. And then for temporal consistency, we have 2 ways. We can do either association of the objects just based on the text annotations, which works surprisingly well. So basically, it's tracking at a higher level. And then obviously, you could do a low-level tracker. And we found that this higher-level tracker works better, but then obviously, you could also combine them. And then here, the data set we have here, these are state-of-the-art data sets. What we can see is that the standard referring expression data sets with STG, HSTD, they actually have annotations in multiple frames, but they only ground one referring expression. Then ActivityNet entities has only annotated the grounding in one of on the keyframe. And then here are 2, the how to ground 1 million, which is automatic, and then iGround, which is manual annotated, where we have annotations on multiple frames and for multiple object grounding put together with the caption. And then here, iGround, this is our manually annotated data set. So here, basically, we have 2,000 trained, 500 val, 1,000 test videos annotated. The annotations are dense in time, and we have multiple objects per frame. We have also multiple raters which have counter-checked the annotations. And then our model, the model is an extension of the GLAM model where we add temporal aggregation, temporal objectness prediction. And so here we have a first stream which predicts the caption here. And then basically once we have the caption, we have a set of multiple queries for which we then predict the bounding boxes and the temporal objectness per frame. So we know actually if the object is present or not. We know which is the time range in which the objects appear and disappear. And then here, some experimental results. We can see here, these are results just with image-based models. And then here we can see that this is on our data set. So this is just GLAM, state-of-the-art method. And then having here our pre-training, even if we evaluate it just on 1 frame, we improve the performance. Fine-tuning further improves the performance. And then if you move to the video evaluation, the second part of the table, we can see here, the first row evaluates our automatic annotation pipeline. So this allows us on our iGround test set to compare how well the different ways of generating this pre-training data works. We can see that here we get an improvement over just having center frame annotations. And then here, if we have used our pre-training and train our model on top of it, it shows actually that it improves the performance, right? The first one is just generating this pre-training data automatically. And the second one is we use the model, train it on it, distill the information from this pre-training set. And you can see that this actually helps us to curate the data. We can do a second round. It further gives a small boost in performance. And then the line afterwards, we just show how the model performs if we just do fine-tuning on this very small data set. And then the last one shows that if we do fine-tuning together with pre-training, it further improves the results. So just pre-training, fine-tuning the model on a small data set is not sufficient. We need this large-scale pre-training data set. And this is also shown here, that if we increase the size of the pre-training set, the performance goes up. And then this is true for pre-training and then also for pre-training combined with fine-tuning. Okay, and then some comparisons to the state of the art. The first table compares to referring expression localization. Our model, which is actually designed for captioning and grounding, outperforms the state of the art referring expression models. And then for spatial temporal grounding, this was work done on the activity and entity data set. Again, we can show that our model outperforms the state of the art. And we can see here, if you look, grow fine-tuning, so activity net entities give some fine-tuning data set, we can show that this outperforms the state of the art. But then basically, if you use pre-training, it significantly outperforms the just fine-tuning approach. So really, this pre-training approach really improves the performance significantly. And then if you look at a few qualitative results, so a person's hands are folding paper graft. You can see that the person's hands in the paper graft are localized well. Here, a person is adding something from a container to a bowl using a spoon. So we can see the spoon here is localized correctly, the container and the person, they're all localized correctly. And so here, a person is cutting meat into pieces by using a knife. So again, the meat is localized correctly, the knife and the hands are localized correctly. Okay, and so basically what we have seen here in this video ground object, that basically now we're able to not only caption the videos, but also ground the objects. And so basically what we hope is that by having this, we can go away from this black box behavior and really using this to design critics by combining grounding and reasoning. So to go in the reasoning step one step further and adding the grounding. We have seen the importance of difficult benchmarks. So it's really important that the benchmarks are difficult. Here we have a benchmark which also gives the reasoning traces, which is important. And then it's also important that the correctness of the benchmark. So we did a lot of tests on some of the state-of-the-art benchmarks, and if they're too easy or allow shortcuts or are badly annotated, it's like not good for measuring the performance. And then the last maybe conclusion is that video LLMs today show strong performance. And the question is really what is missing? One thing which we found is missing, that if you have these difficult questions where you need reasoning, they don't do well. And then the other thing is that if you want to really have this precise spatial temporal localization of objects, events, it's still also not working well. And so you could say maybe this is not necessary, but in the long term, it's necessary, for example, if you want to use these videos for teaching a robot or for embodied AI, or if you want to go away from this black box behavior. Okay, thank you for your attention. And just one small announcement. We have like just a very recent internship opening. So if you're interested, you can send us your application. I've put the email here. Thank you.
Does anyone in the audience have any questions for Professor Schmid? I don't see any questions in chat actually. So
go ahead.
Thank you, Professor Schmid, for the.
I think it was a nice presentation. My question was like, how did you evaluate, the GLAM on the data sets? Because the GLAM was made for static images, not for the videos, I think.
Yeah, this was the table, the bottom of the table. We just evaluated it for the center frame, right? So basically, we just took the center frame and we compared basically the static image part and then the video part. And basically what you can show here is that by adding the temporal information, we get some gain, right? And basically this is nice, but on the other hand, we're not expecting GLAM to do the temporal localization, but we thought it would be like a nice way of comparing to the baseline just to see how it performs on this one static frame. And we can show that by adding temporal information, it adds some smoothing, but what's really important is in the end that we want to have the full temporal annotation, just like a baseline comparison. So
can move on to. Thank you so much.